The universe, the magnificent treasure of infinite mysteries, the unending chain of wondrous and enigmatic phenomena. Man stood, bewildered, in front of these puzzles. From time immemorial, he tried to unravel the mysteries of the universe. Science was his tool. Through endless trial and error, through success and failure, man developed various branches of science. Chemistry was one of them. The extraction of gold from lead, instant cure for all diseases, the ancient chemists had concentrated on such strange targets. We cannot say the alchemists, as they were then known, always succeeded, but they were the ones who laid the foundation for chemistry. As the science of chemistry developed, efforts to develop an effective language to convey the scientific information also began. The effort had started from the time of the alchemists. They used symbols to represent elements and compounds. In 1782, Lavoisier and in 1805, Dalton tried to reform and unify the symbols used. But lack of a unique criterion made the use of these symbols difficult. It was Berzelius in 1814 who organized the chemical symbols as it is used today. For this, he used the Latin names of elements. What is the importance of chemical symbols as the base of the language of chemistry? You might have seen traffic signals, "Do not overtake here," "There is a school nearby," "Drive with care." But if we write these messages in words, it would be difficult for the driver to read. But the traffic signals easily communicate the messages in a universally understandable way. Chemical symbols also function the same way. It is usually first letters of the name of the elements in English, Greek, and Latin. If two elements have the same first letter, along with the second element's first letter, another important letter of the word also is added. For example, since C stands for carbon, we use Ca for calcium and Cl for chlorine. Some elements are given names relating to scientists and universities. Einsteinium, Es, Mendelevium, Md, Nobelium, No, and Curium, Cm. Some elements are given names relating to the names of continents, example, Europium, EU, and Americium, AM. Again, some elements are named after planets in the solar system. The symbols NP and Pu stand for Neptunium and Plutonium respectively. Chemical symbols are like alphabets in a language. If symbols are alphabets, chemical formulae are words. In a water molecule, there are 2 hydrogen atoms and 1 oxygen atom. We can represent this using the chemical formula H2O. But here also we have to make use of certain criteria. Why is the chemical formula of the water molecule H2O? For this, we have to understand the phenomenon of valency. Valency is the ability of one element to combine with another element. This ability or the valency of the element depends upon the number of electrons in the outermost shell of the element. There are 6 electrons in the outermost shell of the oxygen atom. So in order to complete the octet, oxygen combines with 2 hydrogen atoms with 1 electron each in the outermost shell and forms a water molecule. In the case of sodium chloride, sodium atom donates 1 electron from its outermost shell to the chlorine atom in order to form sodium chloride molecule.
Sodium adinte bhagidama shellile 1 electron chlorine vittu kodutha sodium chloride samyuktam undavum.
The valence number of oxygen is 2 and the valence number of hydrogen is 1. The molecular formula of water can be written by interchanging this valence number from each element and writing it at the bottom on the right side of each chemical symbol. This molecular formula H2O tells us even more. That is, a molecular formula represents 1 gram molecular weight of the same substance or mole. What is a mole? How many sodium chloride molecules are there in a crystal of salt? How many copper atoms are there in a piece of copper wire? Or how many water molecules are there in this drop of water? We can easily count the number of these oranges. Same is true with a bunch of grapes. Though a little difficult, we can count these mustard seeds too. But can you count a handful of sand from this vastitude? Impossible. So we could not even imagine counting the number of atoms or molecules. If you bring 1 gram molecular weight of any gas under standard temperature and pressure, each element will have the same volume. For example, if we bring 1 gram molecular weight of gases like helium, hydrogen, nitrogen, carbon dioxide, and oxygen under standard temperature and pressure, each of these gases will occupy a volume of 22.4 liters. This is a phenomenon that led to the development of the mole concept. Molecular weight expressed in grams is known as the gram molecular weight. By 1 mole of water, we mean the number of molecules of water contained in 18 grams of water. Can you guess how many water molecules are there in 18 grams of water? According to the theory developed by the scientist Avogadro, in 1 mole of substance, there would be 6.023 into 10 raised to 23 ions, atoms, or molecules as the case may be. This is called the Avogadro number. Can you imagine a number with 23 zeros on the right side of 6? Perhaps all the sand particles in all the beaches of the 7 seas may not equal it. By 1 mole of hydrogen, we mean 2 grams of hydrogen. 1 mole of water is 18 grams. So, even though the weight of each mole of different elements is different, the number of molecules, atoms, or ions will be the same. That is the Avogadro number. To put it in a simple way, even though the weight of a dozen of oranges and a dozen of grapes will be different, their numbers will be the same. These are examples of substances which have different weights for 1 mole. We can assume the concept of mole from the molecular formula of a substance. Chemical equations are another important part of chemical language. It is possible to compare chemical equations to sentences in our language. Chemical reactions are the simple representation of the complex chemical reactions between reactants to form new chemical products. A chemical equation shows the number and mass of the molecules involved in a reaction. This is the reaction between lead nitrate and potassium iodide. We can summarize the details of this reaction in a chemical equation. This tells us that 1 molecule of lead nitrate reacts with 2 molecules of potassium iodide to produce 1 molecule of lead iodide and 2 molecules of potassium nitrate. Or 1 mole of lead nitrate molecules react with 2 moles of potassium iodide molecules to produce 1 mole of lead iodide molecules and 2 moles of potassium nitrate molecules. The information of these intense reactions of sodium and potassium can be summarized in these chemical equations. 2 sodium atoms react with 2 molecules of water to produce 2 sodium hydroxide molecules and 1 hydrogen molecule. In molar measurement, this would mean 2 moles of sodium atoms react with 2 moles of water molecules to produce 2 moles of sodium hydroxide molecules and 1 mole of hydrogen molecules. We can consider the reaction to make chlorine in a chemical lab. Here, potassium permanganate reacts with hydrochloric acid to produce chlorine and other byproducts. This is the equation for the reaction by which a red rose flower is bleached. Since the mass of reactants and products remains the same in a chemical reaction, when we write the chemical equations, also the masses should be equal. As the mass and number of molecules on both sides of this equation seems to be equal, this can be called a balanced chemical equation. But this equation of the formation of the water molecule from hydrogen and oxygen is not balanced. It will be helpful to compare this equation as an imaginary balance. Here, the number of oxygen atoms on the left side is more than that on the right side. In order to equalize the number of oxygen atoms, one more water molecule can be added on the right side. Now the number of hydrogen varies. The equation would be balanced when one more hydrogen molecule is added on the left side. 2H2 plus O2 gives 2H2O. Balanced chemical equations have great importance in chemistry. One can understand all the details of chemical reactions from chemical equations. Chemical equations play an important role in industry. Using chemical equations, we can calculate the amount of reactants and raw materials required to produce a certain amount of an industrial product. In this way, factories can arrange the production processes in such a way as to minimize material and energy loss. In this factory, titanium dioxide is produced using the raw material ilmenite through various stages of chemical processes. The chemical name of ilmenite is ferrous titanate. Ferrous titanate reacts with sulfuric acid to give ferrous sulfate and titanyl sulfate. It is from titanyl sulfate, the main product titanium dioxide, is obtained. This chemical equation gives a brief summary of the complex chemical reactions involved. From this equation, we can understand that from 1 mole of the reactant ferrous titanate, 1 mole of the product titanium dioxide is produced. To put it more accurately, from 152 grams of ilmenite, 80 grams of titanium dioxide is produced. We have seen that with the development of a chemical language, the study of chemistry became more systematic and easy. With the path this dynamic language opened for us, chemistry is marching ahead towards new horizons of knowledge and discovery.